The reaction between carbon disulfide and chlorine gas reaches chemical equilibrium in a closed container at constant temperature. The products that form are carbon tetrachloride and sulfur dichloride. The balanced equation for this reaction is given below. Initially, an unknown quantity of CS2 and 5 moles of Cl2 are placed in a 2 cubed container and allowed to reach equilibrium. The equilibrium mixture contains 0.8 moles of CCl4. The equilibrium constant Kc for this reaction is 0.36. Question 6.2. Calculate the initial number of moles of CS2 required. And for 8 marks, it means that we need to use a rice table. So let's set up our rice table. R, I, C, and E. So R stands for the ratio of the compounds in this reaction. So we get that from the coefficients. So CS2, in front of CS2 there is a 1. In front of Cl2 there is a 3. Now I like to draw a line that separates the reactants and products. Then CCl4, there's a 1. And S2Cl2 in front, there is a 1. So these are the ratio of the compounds. Then I stands for initial. How much did we have at the beginning? So the information they tell us, an unknown quantity of CS2. So CS2, I'm going to put X here because we don't know how much there was. Cl2, they tell us that there's 5 moles. And it's placed in a 2 cubed container. So at the start, there are no products. So there'll be 0 here and 0 here. The equilibrium mixture contains 0.8 moles of CCl4. So CCl4 is here. And at equilibrium, we have 0.8 moles. Now, this is all the information that we need for now to finish up this table. The important row is the C row, that stands for change. And the change is always in the ratio that the compounds are in. So let's start with the CCl4. It went from 0 to 0.8. It means it increased by 0.8. Now the ratios, so this is S2Cl2, this is Cl2, and that's CS2. Now let's complete this. If this is 0.8, this is going to be plus 0.8 as well, because the ratio is 1 to 1. So 0 plus 0.8, and that's 0.8. Now the reason why I've drawn this vertical line is because everything on the left side is going to be minus, is going to be subtracted. And we're going to subtract in a ratio as well. So if this is 0.8, this is going to be minus 0.8, again because the ratio is 1 to 1. If this is 0.8, it means that this is going to be 3 times that, which is 2.4, since the ratio is 1 to 3. Now we can complete the columns. X minus 0.8 is x minus 0.8. 5 minus 2.4 is 2.6. So this row represents the number of moles of each compound at equilibrium. Now to calculate Kc, we must have concentration. They tell us that the volume of this container is 2 dm cubed. So we can add an extra row for concentration. And all we need to do is divide by the volume, which was 2. So the concentration of each one is going to be just the number of moles divided by 2. So 2.6 divided by 2 is 1.3. 0.8 divided by 2 is 0.4. And that's 0.4 as well. Now we can take all of this information and substitute it into our Kc expression. So our Kc expression is going to be the concentration of my products. So in this case, it's going to be CCl4, and that's 0.4, and it's going to be to the power of 1. And the other product is S2Cl2. It has a concentration of 0.4, and that's also to the power of 1. divided by CS2, which is x minus 0,8 divided by 2, and that's to the power of 1. And Cl2 is 1,3, and that is to the power of 3. The powers come from the ratios. Now we know the Kc value, so 3,6 is equal to 0,4 times 0,4 divided by x minus 0,8 divided by 2 multiplied by 1,3 to the power of 3. We can do some rearranging here just to make it easy to solve. I'm going to take this whole bracket and switch it with this. So x minus 0,8 divided by 2 is equal to 0,4. I'm going to square this since they are the same. Divided by 3,6 and then 1,3 to the power of 3. Now I can simplify and solve for x, and x is going to equal 1,20 moles. And this is the number of moles of CS2 that was added at the beginning. Let's move on to the next question. How will each of the following changes affect the yield of S2Cl2 at equilibrium? And give a reason. So 6.3.1, carbon tetrachloride is removed from the system. What is carbon tetrachloride? Carbon tetrachloride is a product. So if we remove a product, the system will want to increase the product. And the system will do this by shifting the equilibrium position to the right, or you could say it favors the forward reaction. So if the forward reaction is favored, it means that we're going to get more CCl4, and as a consequence, we're going to get more S2Cl2. So the amount of S2Cl2 and CCl4 will increase. Let's move on. The volume of the container is increased. So if they increase the volume of the container, they are decreasing the pressure of the gas particles that are in this container. So if you decrease the pressure, according to Le Chatelier's principle, the system will want to increase the pressure. Now, when it comes to pressure, you look at the number of molecules on each side. So for this side, we have 3 and 1, we have 4 molecules. On this side, we have 1 and 1, we have 2 molecules. The side with more molecules represents a high pressure side, and the side with low molecules represents a low pressure, because there's fewer molecules, fewer collisions. So if the system wants to increase the pressure, it's going to favor the side that has more molecules. That's the left-hand side. So we can say that the reverse reaction is favored. If the reverse reaction is favored, it means that CS2 and Cl2 will increase. And it means that the products, which are the S2Cl2 and CCl4, will decrease. Let's move on. Question 6.4. The graph below shows the changes in the rate of the reaction after further changes were made to the equilibrium mixture above. 6.4.1. The equilibrium was disturbed at 5 minutes due to a change in the concentration of CS2. Was this increased, or was the concentration rather increased or decreased? Now I'm just focusing on this purely from a rate perspective. Since we can see that the rate decreased, it would mean that they removed CS2. Because if they remove CS2, there's going to be fewer particles, fewer collisions, a lower rate. 6.4.2. At 15 minutes, the temperature was changed. Use Le Chatelier's principle to determine whether the temperature was increased or decreased. Explain the answer. Now, we don't necessarily need to use Le Chatelier's principle to explain whether the rate was increased or decreased. If we just know that the rate increased, and we can see clearly that there was an increase in the rate went from here to here. Now, the rate of a reaction will increase if the temperature increases. And that's because if the temperature increases, the particles have more kinetic energy, more effective collisions, and a higher rate. But let's explain it in terms of Le Chatelier's principle. So if we increase the temperature, that's going to favor the endothermic reaction. The endothermic reaction, if we go back to our reaction, the forward is exo because the delta H is less than 0. That means the reverse is endo. So that means the reverse reaction is favored. Now, if we look at our graph, we can see that the dotted line, which is our reverse reaction, increases much more than the forward reaction. So that's the reverse. It increases much more than the forward. So we can see clearly that the reverse increases more than the forward. Again, we don't necessarily have to use Le Chatelier's principle to figure out if the temperature was increased or decreased. We could just answer that by looking at the rate. And in 6.4.3, at what time does the system reach equilibrium after the temperature change? So what we're looking for is where the graphs join back up, where the lines join back up, and where they are parallel to the x-axis. And that's going to be approximately here at 22 minutes.